Download this code from codegive.com, link in the description below. The Pip Williams Outer Limits Central Processing Unit, CPU, a deep dive. This tutorial provides a comprehensive overview of the fictional Pip Williams Outer Limits Central Processing Unit, CPU. Since this CPU is a product of fiction, we'll define its architecture, instruction set, and memory model based on common CPU concepts and imaginative extensions inspired by the outer limits themes of advanced technology and potentially unpredictable consequences. Disclaimer *: This is a purely hypothetical CPU design. No actual hardware exists. This tutorial is for educational and creative purposes, exploring CPU architecture and programming within a fictional context. Setting the stage, the outer limits context. The Pip CPU is envisioned as a highly advanced, experimental processor core at the heart of complex systems explored in the outer limits universe. It's likely to be found powering robotics, advanced androids with sophisticated artificial intelligence. Cybernetics, augmented humans with enhanced capabilities or integrated with machine systems. Artificial intelligence, conscious or semi-conscious AI systems that can be benevolent or terrifying. Experimental technologies, devices that bend the laws of physics or explore unknown dimensions. 2. The architecture, defining the Pip CPU's innards. Let's establish the core features of the Pip CPU. Instruction set architecture, ISA. A custom ISA designed for complex computations, AI processing, and interaction with advanced sensors and actuators. We'll call it OLISA, Outer Limits Instruction Set Architecture. Data width 64-bit. This allows for handling large memory addresses and complex data structures typical of advanced AI and scientific calculations. Registers. The Pip CPU features a set of registers, which are small, fast storage locations within the CPU itself. We'll define the following. R0, R15, general purpose registers for data manipulation and calculations. PC, program counter holds the address of the next instruction to be executed. SP, stack pointer points to the top of the stack in memory. Used for function calls and local variable storage. SR, status register contains flags representing the status of the CPU after an operation, 0 flag, carry flag, overflow flag, interrupt enable, etc. MR, meta register, a special register used for interacting with the outer limits specific meta functions of the CPU, more on this later. Memory model a linear address space of 2 to the power of 64 bytes. This allows for accessing massive amounts of data. Interrupts the CPU supports interrupts, which allow external devices or internal events to interrupt the normal flow of execution. Interrupts are crucial for handling I/O, timers, and error conditions. Pipeline a multi-stage instruction pipeline to improve performance. The pipeline allows the CPU to fetch, decode, execute, and write back instructions simultaneously. Simplified for this tutorial. Meta functions this is where the outer limits element comes in. The Pip CPU has a set of special instructions and functions related to exploring and manipulating the fundamental nature of reality. These are accessible through the MR register and special meta instructions. These functions are unpredictable and may have unintended consequences, mirroring the themes of the outer limits. 3. The OLISA instruction set, simplified examples. Here are some example instructions in the OLISA ISA. This is a simplified set for illustrative purposes. Instruction opcode, hex, Operands description example. Dash 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 dash. MOV01 rightist, RSRC move the value from the source register, RSRC, to the destination register, rightist. MOV R1, R0, moves the value in R0 to R1. LDI02 rightist, IMM load an immediate value, IMM, into the destination register, rightist. LDIR2, 0x1234, loads 0x1234 into R2. Add 03 rightist, RSRC1, RSRC2 add the values in RSRC1 and RSRC2 and store the result in rightist. Add R3, R1, R2, R3 equals R1 plus R2. Sub 04 rightist, RSRC1, RSRC2 subtract the value in RSRC2 from RSRC1 and store the result in rightist. Sub R4, R3, R0, R4 equals R3, R0. Mul 05 rightist, RSRC1, RSRC2 multiply the values in RSRC1 and RSRC2 and store the result in rightist. Mul R5, R1, R2, R5 equals R1 asterisk R2. Div06 rightist, RSRC1, RSRC2 divide the value in RSRC1 by RSRC2 and store the result in rightist. DIVR6, R3, R1, R6 equals R3/R1. Load 07 rightist, address load the value from memory at address into the destination register, rightist, load R7, 0x2000, loads value at 0x2000 into R7. Store 08 RSRC, address store the value from the source register, RSRC, into memory at address. Store R8, 0x2000, stores value in R8 at 0x2000. JMP09 address jump to the instruction at address. JMP0x1000, jump to address 0x1000. JZ0A address jump to address if the 0 flag in the SR is set. JZ0x3000, jump if 0 flag is set. JNZ0B address jump to address if the 0 flag in the SR is not set. JNZ0x4000, jump if 0 flag is not set. Call 0C address call a subroutine at address. Pushes the return address onto the stack. Call 0x5000, call subroutine at 0x5000. RET0D return from a subroutine. Pops the return address from the stack. RET. And 0E rightist, RSRC1, RSRC2 bitwise and of RSRC1 and RSRC2, store result in rightist and R9, R1, R2, R9 equals R1 and R2. Or 0F rightist, RSRC1, RSRC2 bitwise or of RSRC1 and RSRC2, store result in rightist or R10, R3, R4, R10 equals R3 R4. X or 10 rightist, RSRC1, RSRC2 bitwise X or of RSRC1 and RSRC2, store result in rightist X or R11, R5, R6, R11 equals R5 R6. SHL11 rightist, RSRC1, IMM shift RSRC1 left by IMM bits, store result in rightist SHL R12, R7, 2, R12 equals R7 2. Short 12 rightist, RSRC1, IMM shift RSRC1 right by IMM bits, store result in rightist short R13, R8, 1, R13 equals R8 1. CMP13 RSRC1, RSRC2 compare RSRC1 and RSRC2, sets the 0 flag if equal, other flags based on comparison. CMP R0, R1, compare R0 and R1. Int 14 IMM trigger an interrupt with the interrupt vector IMM. Int 0x01, trigger interrupt 1. Meta underscore trans 20 rightist, RSRC, IMM attempt to transfer a property of reality from RSRC to rightist, influenced by IMM. Danger. Meta underscore trans R14, R15, 0x42. Meta underscore OBS 21 rightist, address attempt to observe a property of space-time from memory address and store the result in rightist. Unpredictable. Meta underscore OBS R0, 0xa000. Halt FF halt the CPU. Halt. Notes asterisk. Asterisk rightist, RSRC, RSRC1, RSRC2 refer to register names, example R0, R1, R2, etc. Asterisk IMM refers to an immediate value, example 0x1234, 10, 255. Asterisk address refers to a memory address, example 0x2000, 0x1000, 0x3000. Asterisk the status register, SR, flags are set by arithmetic and comparison instructions. A simplified set includes asterisk Z, 0 set if the result of the operation is 0. Asterisk C, carry set if there was a carry out from the most significant bit. Asterisk O, overflow set if the result overflowed the register capacity. 4. Code example, OLISA assembly. Let's create a simple program that adds two numbers and stores the result in memory. Explanation asterisk. 1. Semicolon denotes a comment. 2. EQU asterisk defines a symbolic constant. Result underscore address EQU 0x2000 means that whenever the assembler sees result underscore address, it substitutes 0x2000. 3. Start asterisk a label that marks the beginning of the program. 4. LDIR0, 0x000A asterisk loads the immediate value 0x000A, 10 in decimal, into register R0. 5. LDIR1, 0x0014 asterisk loads the immediate value 0x0014, 20 in decimal, into register R1. 6. Add R2, R0, R1 asterisk adds the values in registers R0 and R1 and stores the result in register R2. So R2 will contain 30. 7. Store R2, result underscore address asterisk stores the value in register R2 into the memory location specified by result underscore address, which is 0x2000. 8. Halt asterisk stops the CPU. V. The meta-functions, exploring the unpredictable. This is where the pip CPU truly embodies the spirit of the outer limits. The meta underscore trans and meta underscore OBS instructions are designed to interact with the fundamental fabric of reality. Asterisk meta underscore trans rightist, RSRC, IMM, meta transfer. This instruction attempts to transfer a property, represented by the value in RSRC, to another entity, represented by rightist. The immediate value IMM acts as a seed or influencing factor in the transfer. The consequences are highly unpredictable. Examples. Asterisk attempting to transfer knowledge from an alien artifact to a human brain, registers. Asterisk trying to transfer a property of a parallel universe into our own. Asterisk modifying the flow of time locally within a register. Asterisk influencing the behavior of a quantum system. The unpredictable nature stems from asterisk unknown physics asterisk the underlying mechanisms of these transfers are not fully understood. Asterisk chaos theory asterisk small changes in the IMM value or the state of the RSRC can have massive, unforeseen effects. Asterisk non-determinism asterisk the outcome may be inherently random due to quantum mechanics or other unknown factors. Asterisk meta underscore obs rightist, address, meta-observation. This instruction attempts to observe and read a property of space-time from a specified memory address, and store the resulting value into register rightist. The information contained in the specified memory address is interpreted as coordinates in space-time, and an attempt is made to observe the reality that exists at that point. Asterisk example 1 asterisk using it with a meta underscore trans instruction that resulted in unpredictable memory modification. The result can be extremely unpredictable if the memory area contains crucial data. It can lead to cascading system failures or unexpected emergent behavior. Asterisk example 2 asterisk observing the point of origin of a sentient alien signal. This could overload the register with data, requiring a specialized system of decoding. The decoded signal can contain a warning, a request for help, or even a hostile attack pattern. Asterisk example 3 asterisk observing a point in the past. This could violate causality, leading to paradoxes and system instability. The CPU might try to correct the paradox, leading to further unforeseen consequences. Important considerations for metafunctions asterisk. Asterisk error handling asterisk the metafunctions should trigger interrupts on specific conditions, example causality violation, energy overload, instability. The interrupt handler would need to attempt to stabilize the system or shut it down gracefully. Asterisk safety protocols asterisk the use of metafunctions should be restricted to authorized personnel and carefully controlled environments. Asterisk debugging code that uses metafunctions is extremely difficult due to their unpredictable nature. Advanced logging and tracing mechanisms would be required. Example of a program using metafunctions asterisk. 6. Simulating the PIP CPU, conceptual. Since the PIP CPU is fictional, we need a way to simulate its behavior. We could create a software simulator using languages like C, C++, Python, or Java. The simulator would need to 1. Fetch asterisk read the next instruction from memory based on the PC. 2. Decode asterisk determine the instruction type and its operands. 3. Execute asterisk perform the operation specified by the instruction, updating the registers and memory accordingly. The metafunctions would require special handling to simulate their unpredictable nature, perhaps using random number generators or complex state machines. 4. Update PC asterisk increment the PC to point to the next instruction. 5. Repeat asterisk continue the process until a halt instruction is encountered or an error occurs. 7. Conclusion, a CPU of the imagination. The Pip Williams Outer Limits CPU is a thought experiment, a canvas for exploring CPU architecture, instruction sets, and the potential for technology to have unforeseen and potentially dangerous consequences. By combining common CPU concepts with imaginative extensions inspired by the themes of the Outer Limits, we can create a compelling and thought-provoking example of a fictional processor. This tutorial provided a starting point for understanding the PIP CPU. You can further expand upon this design by adding more instructions to the OLISA ISA. Designing a more complex memory management system. Implementing a more sophisticated interrupt handling mechanism. Developing a realistic simulator. Crafting intricate scenarios that demonstrate the power and peril of the metafunctions. Remember, the only limit is your imagination. Just be careful what you attempt to transfer or observe with your fictional CPU, you never know what might happen. Good luck and may your adventures into the outer limits be both fascinating and terrifyingly informative.